Alright, so today's class is going to be Introduction to Ellipses. So as we discussed last time, when we talked about conics at first, ellipse is when you take a cone and you cut it across sort of diagonally. So you have a stretched out circle like you see there. Okay, that's actually a very good example of a cut cone to give you an elliptical shape. Now, for our purposes, we are only going to be dealing with two types of ellipses. We have a vertical ellipses and we have horizontal ellipses. Okay, obviously there's going to be a million more variations. You can have diagonals across any which way, but for our intents and purposes, we are only going to be doing the mathematical calculations for these two types. Now, when we're talking about vertical ellipse, we are talking about this shape. And then when we're talking about a horizontal ellipse, we're talking about this shape. Okay? Now, every single ellipse has four vertices and two major axes. So if we're talking about the major axes, or sorry, two axes, okay, one major, one minor, but we're talking about two axes. So we have one axis that goes right through the top to bottom or side to side. I'll explain why I use different colors in a bit. And then we have another one that goes the opposite direction. Whoa, what happened there? Why did that one change green? Hold on. Back up, back up. I want this to be red. Okay, so now I want to change to blue. There you go. This is what I want. This is what I want. There. Okay. So those are the two axes that exist within an ellipse. On the edge of those axes, so in other words, where the axes meet the ellipse, you have these 4 points here. These are your vertices. Okay, these 4 points are your vertices. So the black dots are your vertices, because we have more than one, so it's not a vertex, it's a vertices. And the blue lines are your minor axes. Okay, which makes the red lines your major axis. Okay, basically what this means is the longer side is called the major axis and the shorter side is called the minor axis. And they always go through the fattest part, or the fattest part or the tallest part of your ellipse. Now what we also have is, if we take half of the axis, it's called a semi-axis. So if we only look at there to there, it's called a semi-axis. Now, why is this important? Well, because it's nomenclature, right? So we have a semi-axis going this way, and we have a semi-axis going that way as well. Anything that's half of the axis is called a semi-axis. Okay, so that being said, this is nomenclature. We are now going to proceed on to, on every ellipse, on every major axis of an ellipse, you will have 2 points. Somewhere around there, somewhere around there, somewhere around here, somewhere around here. These are the focal points of the ellipse. Because there's two of them, we call foci, so same thing there. These 2 points right here. Now, a couple cool things is that they are equidistant from the vertex on both sides. So whatever it is, that's 2, then up here will be 2 as well. Okay, now the other cool thing about this is that if you take any line, let's use a yellow, if you take any line and you connect the vertex to the ellipse and then draw another one from that point to the other vertex, to the other foci, you end up with a line that is the same length as your major axis. I'll say that again. I'll let you write it down. If you add these two lines, let's call that one A, B. No, I shouldn't call it AB because we can use AB for something else later. 1 and 2. If you add the two lines, 1 plus 2, the length of which is equal to your major axis. So is equal to your length of your major axis. Length of your major axis. Now this is cool because it does not matter where you bounce it off the ellipse. I can take the line, bounce it off there, and then to the other one, and it'll still equal that. I can bounce it off straight across anywhere. Let's go almost this way. Boom, and then boom. It will still equal the length of the major axis. Okay, now there's a really cool video on YouTube. Let's see if I can find it for you.
Ever since pool or billiards has existed, mathematicians and physicists have had these thought experiments about mathematical pool or mathematical billiards because it's great for working out how a particle, or in this case a pool ball, will rebound against the sides and where it will go. So I thought, enough of these thought experiments, let's build one. The shape is an ellipse, and ellipses are an interesting type of shape because they can come in an infinite number of varieties. The geometrical property of ellipses, which is why I have made this table, is the fact that if you place a ball on a focus point, wherever you hit it, in whichever direction, I can hit it over there, over there, over there, over there, over here, it will always rebound into that pocket. That is because from any point on the side, it makes the same angle to each focus point. And as you know, when you rebound something against a surface, the angle of incidence equals the angle of reflection. Whenever it is positioned on this focus point, wherever I hit it, it will go in. You know, if it's here, wherever I rebound it, it's never going to go in. It's only when it's exactly on this dot. And so that's the theory, and that what makes this really good fun, and I will demonstrate it. But obviously, I'm a mathematician and I love things to be perfect, but we're in the real world, so now kind of annoying physics gets in the way. Things like friction, things like the difficulty of manufacture. You also have to hit it with just the right force. For example, if I hit it really hard, it rebounds to this side of the pocket. If I hit it a bit softly, it goes to the other side of the pocket. So obviously, if there is the Goldilocks hit, the one that's neither too hard nor too soft, that should get it in, and let's see if I can do that. And I have to say, if I don't get it in, it's really difficult, so you've got to be very skillful. Oh, beautiful. It's so satisfying the way it rolls round and round and round, just reminding me that I've got it in.
Okay, so that video is trying to show that there's basic rebound property there. So wherever you hit it off there, it will always go into the other focal point. So now let's go on to our next slide, or sorry, new picture. No, don't bother saving that one. We are going to give some labels to it. So I'm going to redraw an ellipse. So I'm going to go like this. On it, I'm going to draw my major axis. So it's going to go like this. And I know that on my major axis, I have, where am I? Oh, there it is. I have two focal points. Now, they should be the same distance from the vertices. They might not be because of my bad drawing. But what we have here is that if we had our second axis, which is our minor axis, right through the middle, we are going to label the lengths as such. This length on this side, oops, I don't want that, I want to right. This length on this side is going to be my A, it's supposed to go all the way to the end there. This length up here is going to be my B, and the whole length all the way across the entire ellipse is going to be 2 A as vertically is going to be 2B, to be 2B. Now, what this tells me is that if I have that rebound line, boom, boom, equal to my 2A, if I have that line equal to my 2A, that means that half of that should equal my A. So this means that if I choose this, or yellow lines, those are badly placed. So if I choose to rebound it off exactly the minor axis, if I choose to rebound it exactly off the minor axis, I know that to combine, they will make the length there. So each side is going to be half of my 2A. So therefore, technically, that makes this line my A, right? So does that make sense? If I add both of these lines together, I get 2A, right? Based on what we, the principle from the other screen. So if I only take half of it, I'm bouncing it up right up the middle. So half of it is A. Okay, so now we know that from the distance, from the center of my ellipse to my focal point is now the third side of my right angle triangle, which now I can solve for pretty easily using Pythagorean theorem. So this one we will call C for this case. Even though regularly Pythagorean theorem would have C up here, the math still works. So if you're looking for the length of the focal point, so let's call it the length of the focal point, you are going to use the length of the minor axis. Oh, no, let's do Pythagoras properly. You are going to use the length of the major axis. You are going to use the length of the major axis minus the length of the minor axis square rooted to get the length of your focal point. All right? Now, the other thing we're going to learn today, or we're going to look at today, is that if you draw a line across the focal point that is parallel to your minor axis, these lines are called lattice rectum. Rectum. Anyways, so these lines are called lattice rectums. What is so special about them? Well, they're unique to ellipses. Okay, so the length of these lines you can calculate using the same A and B feature. So go back to home. The length of these lines, so the length of the lattice rectum, is going to be equal to 2b squared over A. That is for this type of ellipse. If you have a vertical ellipse, then the length would be 2a squared over b, right? Because a relates to our horizontal axis, and that refers to our vertical axis. Okay? Now, if you wanted to find the area of an ellipse, this is what you would use. Okay, with your, in this case, your A is your major axis, and B is your minor axis. Or minor semi, sorry, semi-minor, and then semi-major, because the majors are 2 and 2. All right, so that's all the information you need today to do the worksheets that are being given to you now.